Uh, Welcome to lesson 4 of the course on industrial automation and control. So, today we are going to look at temperature measurement. Temperature is a very important quantity, especially in the process industries. All big process plants like chemical plants, steel plants, for them monitoring of the temperature is very important. So, we will see how these measurements are done both in the online and the offline case. Looking at the instruction objectives, the first one is of course that there are various principles of operation of the different temperature sensors. So, the student will be familiar with that. He or she will be able to describe the various signal conditioning aspects, as we have already discussed that measurement involves transformation from one variable to another till the measurand or the variable of interest comes into an electrical form, so that it can be used very easily. So, for that you need signal conditioning and processing, and they are specific to the kind of sensors that are used. So, the student will be used to describe the signal conditioning aspects, the major applications of each sensors, the situation in which these can be used, and finally they will be able to explain the comparative merits and demerits, and will be able to, hopefully they will be able to make an intelligent choice of a sensor given a practical situation. So, these are the objectives of this lecture. So, we come to temperature measurement and why it is needed. It is needed for various purposes. Firstly, it is needed for control. Typical example would be a heat exchanger. So, in a heat exchanger we want to control the temperature of in a heat exchanger there are generally two streams. One stream which is called the cold stream, which is getting heated, and another is a hot stream which is heating. So, generally we need to control the outlet temperature of the cold stream. So, for that we definitely need a temperature feedback, and that will involve temperature measurement. Similarly, for a reactor, because most of the chemical processes, the reaction rate and the pressures inside the reactor, these are all related to the temperature. So, the temperature is actually a very important quantity to monitor and measure for reaction control. Similarly, for supervisory control, there are, for example, suppose you want to roll a hot steel bar. So, you are going to actually pass the bar through two heavy rolls, which will press and flatten the bar into a thinner piece, right? That is called rolling. So, it turns out that obviously the rolls are going to experience a lot of force. They are going to push the bar so that it gets flattened. Now, how much force is actually required depends critically on the temperature of the bar. If the bar becomes too cold, then an undue amount of load will come on the rollers, and which may also break. In fact, this has happened. I'm personally aware of situations where this has happened, basically because the operator, before he was trying to move the bar into the rolls, there was no temperature sensor which could tell him that this bar is suitable to be rolled. Its temperature is beyond a certain minimum value, right? So, he was pushing any bar through the roll, and that was sometimes creating tremendous force on the roll, because the bars were cold and the rolls were breaking. So, this is supervisory and operator controls. Operators many times perform operations looking at the temperatures. For that you need temperature measurement. Temperature measurement is very much needed for safety as well as energy efficiency. Energy efficiency is actually a very critical task, because large thermal processes take a lot of energy, and much of the cost of the production comes from the energy cost, which is rising all the time. So, one needs to ensure that heat is not lost, it is optimally utilized. So, for such purposes temperature has to be monitored at various places on the plant. Similarly, safety, because temperature is often related to pressure and other things. So, I mean a very high temperature may lead to burns, it may lead to overpressure, it may lead to explosions, it may lead to various things. So, safety and energy efficiency, for these purposes temperature measurement is needed. Similarly, the temperature measurement may be needed in a variety of applications. So, for example, a variety of ranges below 100 degree, below 0 degree, above 0 degree, several hundred degrees, at various accuracies, at various resolutions, and in various kinds of environments. Some of them may be inert, some of them may be oxidizing, some of them may be reducing, some of them may be corroding. So, these are there are various kinds of application features which one has to keep in mind when one selects a temperature sensor. Since we are talking about control and since this course is mainly about control, so one has to also mention that remember that temperature measurement generally involves time constants, because it involves thermal time constants of various things including the sensor. And so, the thermal time constant of the plant is there, but sometimes if you assume that the temperature measurement temperature sensing is going to be instantaneous, then that is an error, because in many cases the sensor itself contributes non-trivially to the overall time constant, and that can affect control performance. Similarly, non-linearity, there are sensors which are highly non-linear and one has to keep in mind. Apart from that fact, it also affects accuracy. There could be noise associated with temperature sensors also. Basically, noise sometimes comes with if you are trying to measure temperature in a flowing fluid because of flow turbulence and other things. So, having said this as the introduction, let us look at the various temperature measurement strategies. So, you can divide them into basically two parts, one is contact, another is non-contact. So, in the contact part, the thermometer usually comes in contact with the medium at which you want to measure the temperature. So, for example, simplest ones are expansion thermometers, either solid expansion or liquid expansion or gas expansion thermometer. So, you have in solid you have these bimetallic thermometers, in liquid you have the well known liquid in glass thermometers. Generally there is a spelling mistake here. Generally we have mercury in glass, sometimes we can have ethyl alcohol in glass and things like that. We have gas and vapor thermometers and other than that we have generally resistance variation is a very standard phenomenon, resistance variation with temperature, which is utilized for temperature measurement. So, we have generally have two kinds of sensors here, one is called a thermistor, which is actually a semiconductor resistance, and the other is a metallic resistance like resistance temperature detector. So, we are going to look at these two. Apart from that, there is something called thermocouples, which basically rely on the fact that thermoelectric EMFs are generated when one of the junctions of two dissimilar metals are put into a high temperature. So, that EMF is measured and used as an indicator of the temperature of the so called measuring junction. We will look at all this. Similarly, among the non-contact types, we will look at the radiation pyrometer, which basically does not directly get into the mediums always, but sometimes can take the radiation out from the medium, maybe through a window or through an aperture, and then that radiation itself is used for sensing the temperature. So, such things are called radiation pyrometers. Let us start with resistance temperature. Among these classes, the so called expansion thermometers are we are going to put less stress on, because they are not they are generally used as indicating instruments and not so much used for control or automated monitoring. So, therefore, we will begin and put more stress on the resistive temperature sensors and the thermocouple, because they are easily integrated with the control and automation equipment. Coming to resistance temperature detectors, these are simplest, these are basically metals and we know that the resistance of a metal varies with temperature. And although the temperature ratio, I mean the temperature relationship can be quite complex, but it is generally sufficiently accurate to model it as by this form, in which, so RT, this T is actually a temperature difference. So we are writing R0 is resistance at 0 degree centigrade. It's not always necessary to make it at 0 degree centigrade. You could have it at some RT0. So if the resistance at temperature some T0, in this case we have assumed 0 degree centigrade, is R0, and if the small t is the temperature difference between the temperature at which you want to know the resistance, suppose it's capital T, then small t is equal to, we can also have, this is a generalized, this is this special case where R0 is assumed at 0 degree centigrade, but in general you could have R0 is resistance at, you can write it as RT0 and RT, then you will have the formula RT is equal to RT0 into 1 plus alpha into T minus T0 plus beta into T minus T0 square. This is the general form. In this case, since we have assumed T0 to be 0, so it is coming to be this form. So the small t is actually, though it is said that is resistance at T degree centigrade, actually this small t stands for the temperature difference between this one and this one. Okay. So, so in other words, it is sufficiently accurate. So in fact, this coefficients of alpha and beta, if you see, they are actually constants. For example, look at one of the metals which are typically used is platinum. See that beta is actually very small, very small, and beta comes into play only at very high temperature ranges. Otherwise, compared to alpha, it is about 10 to the power minus 4 times small. So therefore, it is the response, if your temperature range is not too large, then the response is largely linear, and well, you can always compensate for that, and therefore it is for this reason that these sensors are very popular, and they can be used as more or less linear sensors, except in certain metals like nickel. So typical metals which are used, for example, are platinum, nickel, copper and tungsten, and they can be used in various ranges, basically depending on environmental conditions, depending on melting points of the metal, etc. And you get quite good linearity. For example, if you see the resistance temperature, how the resistance ratio increases, then you find that for copper, platinum and tungsten, they are more or less linear, while for nickel it is somewhat non-linear, although it is the most sensitive. And then of course nickel and copper are much cheaper than platinum, so therefore except in critical applications where you really need to know the temperature accurately, you don't use platinum. For example, in most of the air conditioning applications, this building air conditioning applications, people generally use nickel RTDs because of the fact that it is the cheapest, and anyway the application is not so critical, it does not demand a very high level of accuracy. Range is also range of temperature variation is also small, so in that range nickel can be assumed to be linear. So if you want to, so you have a resistance here whose resistance, you have an element whose resistance value changes with temperature. So now how are you going to generate an electrical signal out of this resistance value? One of the simplest things, as we have seen, to convert a resistance value to a nearly proportional voltage value is the Wheatstone's bridge, is the DC Wheatstone's bridge, which looks more or less like this. So it is well known, and I am not going to cover this here, that this detector voltage across the detector for small changes in this RT, which is the sensor, are going to be proportional to the resistance change. Now here note that although it looks like this resistance is drawn in a slightly different way. This is just to emphasize the fact that while actually this bridge will be possibly somewhere in the control room. So from the control room, two long pieces of wire and there those two pieces of wires will actually go to the field and connect the RTD. So these are actually long pieces of wire which must be realized, these are called the lead wires, and since they go through various places, so temperature can vary along their path, and the resistance of these lead wires can also change, and as far as this detector is concerned, the detector is going to interpret that as a temperature change. So this is called a lead wire error which can occur. So to prevent this, the standard strategy is to go for a 3-wire method of measurement. You can go for either a 3-wire method or you can go for a 4-wire method. So in a 3-wire method, the principle is simple. The principle is that, see, you have 3 wires now, this, and this. So actually what happens is that the current, look at the current flow path. The current flow path is through this path. So that flows through this one. While the detector actually senses the voltage across these two. So what happens is that this lead resistance is variation, that is, if there is a variation across this lead resistance, that does not affect it, right. So similarly you could have 3-wire or you could have 4-wire RTDs where you could again run another piece of wire from here, you know. Right. So no, if you have a 4-wire RTD, then you could have a very simple circuit, that is, you have a battery and you have an RTD here. So you have 4 wires and you have 2 wires, here you have the voltage. So you see that through these wires are also long, but they are the current carrying wires. So these are also long, but they don't carry current because this is a voltmeter, so it's a high impedance thing. So therefore you actually sense the potential across the resistive element only and not on the leads. So if you have a 4-wire RTD, then you can use this circuit. This is the 4-wire method. So by these methods you can actually take care of the lead wire problem. Let us look at a typical specification of a platinum RTD. This is just to show that you can get a very accurate sensor. See, the error is plus minus 0.05 degree centigrade over this range, and the repeatability is 0.02 degree centigrade. This is another very great thing about platinum, is that it is a noble metal. It's not degraded easily, and it's possible to obtain it in very high purity, and it is interchangeable. That is, if you take 10 readings, you will get the same readings, and even if you replace the sensor by another so-called identical sensor, you will really get identical performance. So that's very important thing in the industry for which it is used. Just to give you an idea, the RTDs are actually, these resistors are actually put inside probes, and we'll show how they are put inside probes. So these are various kinds of probes are available. So you know, if you want to measure temperature of air or gas, then you need to ensure that the flow fluctuations do not cause temperature fluctuations. So you actually put the probe, and then outside you put another cylinder with some holes such that the fluid inside it, whose temperature is actually sensed, that is not so much affected by the flowing fluid. So that's why you have, when you are trying to measure the temperature of air or gas, you have this kind of probes. Sometimes you like to penetrate the probe into something and measure the temperature inside, or you could have a general purpose tip which is just fixed to the medium. Inside the probe, the arrangement is like this, that you see you need to increase the resistance, right, to about 100 ohms. So you need to have very thin wires and you need to have very long wires. So the thin and long wires are actually arranged like this. So they are coiled coils. So there is a former which is like this. So on that, this thin coiled coil is wound, and it is important that it is not stressed, because if it is stressed then it may tear. So it is neither stressed by expansion, etc. And then you need to ensure that you have very good conductivity between this. Here is the medium. So the heat must flow through this space and then reach these elements. So for that you need to fill this element with good conducting material. Sometimes you use ceramic powder. So this is how it looks like inside. So this is about the RTD. It is a very simple instrument. The next one is the thermistor. The thermistor is actually a temperature sensitive semiconductor resistor. So they typically have negative temperature coefficient, which is interesting. Although there are positive temperature coefficient thermistors are also available, but they are less used. The advantage of the thermistor is that the resistance change is very large, so you get great sensitivity, but it works in a small range. After that, semiconductor material, so cannot withstand too much temperature. It's also very non-linear. That's a drawback. But it has very small size, and therefore it has very small thermal inertia, so it can measure very quick temperature fluctuations and can reach various small places. So that for that it is used. It is generally made of oxides of manganese, nickel, cobalt kind of materials, and it is available. It's actually you make a paste kind of thing, and then on a piece of wire you make lumps of that paste, and then you connect it on the wires, and then you sinter it. So if you sinter it, then this piece of material on the two wires, they actually form the thermistor. So if you see the resistance temperature relationship, it's highly nonlinear. As you can see, it's an exponential relationship, and R is again resistance at some T degree Kelvin. R0 is resistance at some T0 degree Kelvin, and therefore this is related like this. And beta is called the thermocouple material constant. Varies from 3000 to 5000. We generally take it as 4000. If you differentiate this, that is find delta R by R divided by delta T, that is percentage change in the resistance for unit change in the temperature, you get this expression which shows that the sensitivity changes drastically with temperature. So at low temperature it has very high sensitivity which quickly comes down and becomes flat. So here you have the sensitivity characteristics are shown. So the resistance temperature characteristics, this is just a form, we have not drawn it to scale. So for negative temperature coefficient, with temperature the resistance comes down, and for PTC or positive temperature coefficients, up to some temperature it stays at a lower value and then suddenly increases. PTC are generally used for for switching applications, generally not used for measurement. Since it's a resistance, it can be again put in the Wheatstone's bridge, and it turns out that you can derive this expression delta RT by RT, which is the percentage change in the resistance, is given by 4 E0 by Ex into 1 minus 2 E0 by Ex. So if you get E0, these are all constants. So what happens is that now if you know that the beta by T square. So from here, so this is what you can sense. So from E0 you can sense this delta RT by RT, and then based on your sensitivity you have to find out what is the temperature. For small ranges, that is when the overall temperature T does not change too much, minus beta by T square can be assumed to be constant. So in that case the percentage change in resistance is proportional to the temperature. In this case there are certain advantages. For example, the resistance itself is much larger compared to the lead resistance, and its change is also quite large. So therefore the effect of lead wire resistance variation is not very negligible here, not so significant as in RTDs. But on the other hand, there could be self-heating error. You see, self-heating error typically occurs much more in negative temperature coefficient thermistors, because when current flows through this, if a significant amount of current flows through this, it will cause heating. Now as it will heat, that will bring its resistance lower. When its resistance becomes lower, then more current flows, and more heat is generated. Now this situation can actually run away, and continuously the temperature of the thermistor will increase, so you will get a much erroneous temperature, and then finally the device may burn. So it is needed to ensure that the current does not go beyond a certain level in the NTC thermistors. There are certain, you can actually connect certain amounts of resistances in circuits like this, which are called linearizing circuits, and then tune these R1 R2 values such that over a range this combination resistance, that is this E0 will be, E0 is going to be linear with T. So you basically in this equation you have RT is known, I mean the variation of RT. So you have R1 and R2 unknown. So you based on linear variation you try to ensure you choose the values of R1 and R2 such that you get the E0 values on a linear curve for this thermistor. So there are, if you put that, then over that range it is expected to be roughly linear. So linearity is, but at the same time we must remember that linearity improvement is at the cost of sensitivity. This you can easily check by simply putting a resistance R across RT, a fixed resistance R across RT. You will find that the sharp variation of variation of fall of resistance will become much more linear, but you will also know that the sensitivity has changed. Now for unit temperature change the resistance does not change by so much. So you can gain some improved linearity at the cost of degraded sensitivity. These are some of the RTD probes, thermistor probes. So you can see again same thing. This is a gas probe again with a head, and these are these are exposed RTD bead, thermistor bead, and you can have various kinds of probes here. Here you will find that if you compare these values, then you will find that firstly you will find that the range is much smaller, the resolution is good very much, but the accuracy is much degraded compared to the RTD. So these are the characterizing features of a thermistor. So here are these two resistive sensors. One is a metal resistance, another is semiconductor resistance, and you basically use Wheatstone's bridge, and they have trade-offs regarding sensitivity, linearity, range, etc. After that we come to thermocouples, which are based on the principle that if two metals, so you have metal A and metal B, if they are joined at these 2 points, and if these junctions are maintained at and if the junctions are maintained at temperatures T1 and T2, then what happens is that here you will get an EMF. This effect is called the Seebeck effect, and this EMF that is generated can be related by some polynomial like this, and people use 7th degree, 8th degree polynomials to catch this resistance variation, right? This EMF variation, this is called a thermoelectric EMF or thermo EMF. So you see, by sensing this EMF you can actually sense the temperature. The advantage of these, there are 3 kinds of EMF, strictly speaking, from a physics point of view. There is one called the Seebeck effect, which is the basic effect which is used in the temperature measurement, which says that at the junction of two dissimilar metals, an EMF, which is a function of the junction temperature difference, actually exists, which is a function of junction temperature. So now if you have two junctions at two dissimilar temperatures, then there will be two different valued EMFs, and so there will be a potential difference across these 2 points. So this is the idea. But there are 2 other effects associated. One is called a Peltier effect, which it comes into play when current flows through the junctions, and due to the thermoelectric conversion process the junction temperature may get changed slightly, and because the junction temperature changes slightly, again by due to the Seebeck effect the EMF can change slightly. So the Peltier effect can affect the measurement, although it does negligibly because hardly any current flows through a temperature measurement junction because they are usually connected to a very high impedance point on a meter. So Peltier effect is generally negligible. Similarly, you have Thomson effect, which comes into play if there exists a temperature gradient along the metals. Then you have another EMF which is developing, but this is also not so important. So therefore, for the case of temperature measurement, Seebeck effect is the main effect which we are going to look at. There are various laws of the thermocouple circuits which make the thermocouple a very useful instrument. For example, the first three says that it is only dependent on the junction temperature. So T1 and T2. Even if there is T3 here, T4 here, T5 here, these arbitrary temperatures can exist here. But as long as the junctions are at T1 and T2, then the EMF is going to be the same. Right? So these two cases will give same EMF. Similarly, it says that even if you connect a third metal here and the temperature here can be anything, but still if you have here if you have A and here if you have A and this is B, and if you maintain them at the same temperature as T1 and T2, then you get the same EMF across the loop. That is also another point. The third point says that is basically a similar thing, only thing is that you are now opening out the junction itself. So rather than having a junction, you can have an extended junction. So you can call this one as the junction, though it is not a physical junction. The junction is actually through another metal, arbitrary metal. Even then the EMF is the same. So the insertion of a metal, and we need not bother about as long as we keep the junction temperatures the same. And we also need not bother about the temperature gradient across the wires. We only need to bother about the temperatures at the junction points. So that makes measurement much easier, because if we had to maintain the temperature all across the wire, then it would have been much more cumbersome. Next, say that the measurements are, so you have two rules. One is called the law of intermediate metal and the law of intermediate temperature. So it says that if you have between A and C, when you maintain them, see these three cases, you have the same temperature T1, T2, T1, T2 and T1, T2. So temperature difference is the same. Now if you connect A and C, you get a EMF E1. When you connect C and B, you get E2. So it says that if you connect A and B, you will get E1 plus E2. So which means that you can connect. So it means that each one of them, the EMF can be calibrated with respect to a particular metal, and then we can make arbitrary combinations of these, and then using this law we can find out what is going to be the EMF generated. Right? So that's a big advantage in standardization. Similarly, it says that this is superposition holds here with respect to temperature also. So between the two same metals, if you have T1, T2 junction temperatures, then you get the first one. If you have T2, T3, you get the second one. So if you have, actually this should have been E1 and this should have been E2. So if you now maintain T1, T3, then you will get E1 plus E2. So they just add up. So it's very linear and it's very easy to measure the temperature. So you can have, there are various kinds of thermocouples. They are typically called, called by some industrial type names like, J, K, T, S. So K type thermocouple is a popular one. It's called chromel-alumel. It has got a good sensitivity and a decent range. So it generally measures in this range. Similarly, you can have copper constant, and which has, the only problem is that the range is lower, basically because of the fact that copper gets oxidized and corroded beyond this, and there is also some variation in the sensitivity. So the sensitivity is not, so that means that there is some amount of non-linearity there. Similarly, you can have iron constantan, which is type J. See the large range and the good sensitivity. The type S is the most stable. It has the highest range, which is platinum 10% and rhodium is one wire, and pure platinum is another wire. This is very stable, can measure temperature up to 1400 1500 degrees centigrade, but has very low sensitivity. So this is just to give you some examples of some typical thermocouples. Now yes, now the point is that we are not interested, as we have seen, that the thermocouple can measure the temperature difference between the junctions. Now we are not interested in measuring the difference, we are interested in measuring the temperature of the measuring junction. So what are the ways? Oh, this needs to go back. Okay. I'm not okay. So I think I'm missing one slide. That's why I'm wondering. So anyway, so you see there are basically two strategies. If you want to get the temperature of the measuring junction, one strategy is that keep measuring junction at 0 degree. Keep reference junction. One of those junctions is called the reference, or sometimes called the cold junction, at fixed temperature. That's one way, but then that is cumbersome, because you need to how do you maintain temperature there? So you either have to put it in a small oven, or you have to create some some ice bath in which you are going to dip it. So that's cumbersome. So therefore, what people try is that the voltage drop which occurs due to the ambient, suppose you keep the reference junction in just open, so the temperature in the ambient is going to vary, and that will cause some error. So what you should do is that you must compensate for the ambient temperature variation using electronics, and by measuring the ambient temperature variation. That's the smart way to do things, which is also much easier. So what happens here is that, you see, if you look at this circuit, what happens is that this voltage actually becomes Vt minus Va. So it is not Vt, because of this is the ambient, so it becomes Vt minus Va. So basically what we are trying to do is that at the output we are trying to add this Va. Basically that's what we are trying to do. So how is that being achieved? See, we have put a sensor which is called a AD590 sensor. It has a 1 microampere per degree Kelvin sensitivity, so it delivers current 1 microampere per degree Kelvin. So and this is 2.5 volt. So at 0 degree centigrade it is going to put 273 microampere. When that will drop through this potential will become 2.5, and this is also 2.5. So you see that so this is also 2.5. So this potential is the same as this potential. So therefore E0 is normal. But now as this temperature rises, the potential at this point will change by how much? For Rn constant, and it will change by something like 52.3 microvolt per degree centigrade. Microvolt per degree centigrade. So we have to compensate this. So that's why a 52.3 ohms resistance is put, so that every additional microampere will now drive through this, right? So this, what is going to happen is that this point will be at a higher potential compared to by exactly 52.3. So as this potential falls, this potential is going to rise by the same amount. So the E0 will not be affected by the change in this Va. This is what is cold junction compensation. So there are various advantages of thermocouples. For example, they can work over long range and give relatively large thermal EMFs, and they can be precisely calibrated, and they are generally resistant to corrosion and oxidation, and they are interchangeable. So these are basically advantages of using thermocouples in an industrial situation. Similarly, if you connect many thermocouples in series, you can further increase the sensitivity of the thermocouples. And so if you put many n number of measuring junctions, then this voltage will be n times the voltage that you can get from a single thermocouple. So that's called a thermopile. This is a picture of a typical thermocouple based meter. See, this is a probe, and these meters are constructed such that you can connect various types of thermocouple, J, K, T. You get pretty good accuracy, which is 0.1% of reading over this range, 0.1% of reading, or plus minus 0.3 degrees centigrade. So you have various other electronic features also. So these are very popular instruments which are used in the industry. So having seen these are the main types of sensors which are used. So apart from this, there are very well known temperature sensors, but we are not going to put much stress on that because of the fact that they are not so much used in automation as such. They are generally used for indication purposes. So for example, we know that the well known liquid in glass thermometer. So here is a liquid in glass thermometer which is shown in an sort of an industrial casing, So liquid in glass thermometers, you have to have, there are very precise markings available, and there are immersion points marked that you have various kinds. You have the total immersion type, you have the partial immersion type. You mostly use mercury. Sometimes you can use ethyl alcohol, etc., which have much higher expansion coefficient. So you get better sensitivity. But generally they are all of manual reading types. Although there are some versions where you try to sense that a mercury column is rising, or you put a slight light float in the fluid which also rises, and then you can, using some proximity detection principle, you can automatically detect the temperature. But generally these are manual reading types, and so therefore we are not going to cover them in too much detail. So these are based on the expansion of solid, liquid, gas under temperature principle. So the liquid expansion thermometer is the most common. So we told that first. Then you have solid expansion thermometers, which are basically bimetallic strips. So depends on the fact that the expansion coefficients of the two solids are actually different. So therefore, if temperature increases at one temperature, they have no stress among them and they are bonded together. So if temperature decreases, it will turn one way. If temperature increases, it will turn the other way, right? So therefore, from this motion, we can measure temperature. And there are industrial sensors which actually utilize this kind of bimetallic sensor. They are sometimes also used for temperature switches, and sometimes they are used as bimetallic springs. So as the temperature rises, then the spring rotates, and it can be connected to something like a dial. Similarly, you can have gas expansion and vapor expansion thermometers. So this relies on the fact that the vapor pressure of a liquid depends on the temperature. So this pressure is actually sensed by a pressure sensing device. In this case, we have shown a capillary and then a Bordeaux gauge kind of thing. So as this vapor pressure increases, this spring will turn, and then that will create an indication. Similarly, for a gas pressure thermometer, so here you have a bulb which is essentially a constant volume case, because the capillary volume you can neglect. So the pressure increases linearly with temperature, and this pressure is again sensed by a pressure sensor in the same way, and you have this is a picture of an industrial sensor. One of the non-contact methods which is which is interesting and used in many cases, especially when you need to measure temperature from a distance, or when the temperature is too high, like you want to measure the temperature of interiors of furnaces, where even putting a thermocouple can be very difficult, or you want to measure temperature of molten steel. Then if you dip a thermocouple, it will give a reading, but it will get immediately destroyed. In fact, thermocouples are used in such cases, but modern techniques of measurement are trying to utilize the fact that a heated body gives out radiation, right? So let's go to the theory first and just find out the idea. So the idea is that a heated body gives out radiation, and this radiation depends on two things. That is, the radiation is actually spread over the radiation frequencies or the wavelengths. So you have what is known as a power spectral density at a given temperature, which is given by this formula, right? So if you this is you can say that WBB for black body. So this is a sort of an idealization. So a black body at wavelength lambda and temperature T gives a radiation between lambda and lambda d plus lambda. It will give a power which is this one into d lambda. So the power between lambda and lambda plus d lambda is equal to WBB lambda T d lambda. So if you want to find out the total power, then you have to integrate this lambda from 0 to infinity. So that's what has been done here, and you get it only as a function of temperature, which is Boltzmann's law. So this is the Stefan-Boltzmann constant. So now what it turns out that ideal real radiating bodies are not black bodies. Black bodies are an idealization of physics. So the body could be ideal. You need to apply some kind of a correction factor to the black body radiation to get the actual radiation from that body. So that correction factor is called the emissivity. So the emissivity of a given body A is the ratio between its actual thing and the theoretical black body power spectral density. So if you take the black body power spectral density and if you multiply it by its emissivity, then you get the real power. Or in other words, the black body one can be obtained by taking the real power and then dividing by the emissivity. So now let us see how we actually collect that radiation. So what we do is, for example, suppose you have a radiant medium here. So the radiation, in this case we are using an optical fiber. This is a particular case. You have various kinds of radiation parameters. You have optical radiation parameters. You have. So basic idea is that you collect the radiation and then focus it onto a sensor. So if you focus it onto a sensor, then the temperature at that sensor is going to go high, and then you use such sensors are generally conventional sensors. So they could be black coated particular strips of metal which are called bolometers, or they could be thermopiles, or in this case this is a case which is a slightly modern case where you are actually collecting the radiation from a long distance using an optical fiber. So the radiation gets in to the fiber here, and it gets into the fiber here and then travels through the fiber and then finally comes to a lens. Now this lens will focus this power, and then here you have a monochromatic filter which actually will take a particular lambda. So only a particular lambda will actually pass through it, and then this radiation will fall on this diode. So the current through the diode, because this radiation is going to cause some free electrons in the diode, and therefore the current through the diode will increase. Now this current has been amplified using an op amp, so that will give rise to a voltage. So this is the principle of measurement of radiation pyrometer, and there are a number of variations possible. So, so that is about we have come nearly to the end of the lecture, and okay, so this we have seen. So this is then the next one is emissivity, and you have very good, this is a picture which shows an infrared thermometer. So you basically you have something like a, in this case you don't have optical fiber, but you actually directly point this gun. Often they come in the form of pistols. So you just point the pistol towards the object, and the radiation from that side of the object will be sensed. And if you keep it at a certain known distance, then it will give you the temperature. Sometimes it is used to, it is in many cases it is used to also detect places where there is steam leak, or there could be some electrical power panel there is some current related heating is being generated. So you just, if you take the instrument and just rotate the gun, you will know that where you are getting hot spots. So that is sometimes useful in, especially in maintenance and other related activities. So we have come to the end of this lesson. Before we close, we need to review it. So we have looked at temperature measurements briefly, of course, and we have basically looked in some depth on resistive temperature sensors of two kinds. Firstly, we have looked at RTDs, which operate at longer ranges and are very stable and give rise to accurate instruments, but their sensitivity is not that high. And on the other hand, we have seen the thermistors, who are semiconductor resistances, the quite nonlinear, so therefore can be effectively used in low temperature ranges, but is highly sensitive and with a very low thermal time constant. So therefore, quick and rapid temperature variations can be sensed. So apart from these two, we have seen the RTDs and thermistors. Apart from these two, we have seen the thermocouples, which are a sense of which are active sensors. So active sensors means that even without power, they generate some source, while this RTD is actually a passive sensor, because to be able to generate a voltage or a current, it requires a power supply. So we have seen various kinds of thermocouples. Thermocouples also are very stable and operate across a large temperature range. They are also pretty accurate. So therefore, they are actually widely used in the industry. One of the there are some problems associated with thermocouples, especially when you have long lead wires. These thermocouple wires, they sometimes suffer from electromagnetic interference, electromagnetic as well as electrostatic interferences. So they have to be properly sheathed, and sometimes so and sometimes for better, generally thermocouples are wired, so they are not mechanically very strong things. So they are sometimes put inside thermo wells. So you actually have, so suppose this is a structure, you actually have a thermo well, and then inside the thermo well, as we have seen in the case of RTD, so you have a protective material, and then inside you actually put the thermocouple wire. Now this thermocouple wire, so sometimes you can keep it like this. So here you form the junction. Junction is generally formed by welding or by brazing, and sometimes you want for better heat conduction, you sometimes ground this. So you can have grounded junction type thermocouples, or you can have ungrounded junction type thermocouples. Accordingly, you will have to when you interface it with an amplifier, thermocouple voltage essentially has to be amplified. There is no other signal conditioning needed. So some filtering and some amplification is needed, standard filtering and amplification. Apart from the thermocouples, we have seen the expansion thermometers, all kinds, although they are not so much important for industrial automation. And finally, we have seen what is basically a radiation pyrometer. So points to ponder: you can mention two conditions for temperature measurement by thermistors. Under what condition? We have told it many times during the lecture. What happens if the cold junction of a thermocouple is kept at ambient temperature? So why do you do cold junction temperature compensation at all? What is the preferred signal conditioning method for resistive temperature sensors and why? Why always Wheatstone's bridge? What is the basic advantage of Wheatstone's bridge? When is an RTD the appropriate sensor? When is a radiation parameter appropriate? And finally, if you can mention one drawback of expansion thermometer. So you can ponder over these. Answers are generally available in books and also in this lecture. Thank you very much. Welcome to lesson number 5 of the course on industrial automation and control. Today we are going to talk about pressure, force and torque sensors. These sensors are used in a variety of contexts, both for the process industry as well as the manufacturing industry. So let us look at the instructional objectives as is the practice first. So the instructional objectives are the following. Number 1, to understand the basic principles of operation of various pressure gauges which work in various pressure ranges. To describe the principles of operation of different force and torque measurement systems, and most of them use, many of them use the so called strain gauges. So to understand the basic principle of measurement with strain gauges. So it turns out, as we have learnt earlier, that when we want to get the value of a physical variable from one form to an electrical form which is convenient to sense, to process, to display, this transformation from the variable that we want to actually measure and its electrical form actually goes through a number of stages, as we have learnt. So it gets transformed to some intermediate forms, and these transformations, each of them in turn, are sometimes achieved through sensors. So in an overall measurement system, you often find that there are a number of sensors